Hello everyone, welcome to the fourth live session. So, uh, Today we will be solving yet another set of problems, and let's begin with the problem solving sessions. So, the first problem it states that we have two semiconductors, semiconductor A and semiconductor B, and the semiconductors A and B they have some effective density of states. Okay, that is, actual density of states will be uh, uh, some number which will start just at the, let's say, if we are considering the conduction band edge, as is the case in this problem. So effective density of states will be the density of states that are present, and there is a just mathematical representation of all the states that are present in a particular semiconductor. So we are considering as if all the states are present at the conduction band edge. So that's why we are saying that they are effective density of states, not the real density of states. Okay. If we consider the real density of states at the conduction band edge, you will see that it is zero. Okay. If you just plug in the numbers as well in the formula that we, or in the expression that we obtain, we will find that the density of states at the conduction band edge is zero. But this is a mathematical tool to us. It helps us to make our life easier by considering all the states present at the edge of the conduction band or at the valence band. So this problem states that we are having two semiconductors A and B, and both are having the density of states, a same effective density of states. Effective density of states, as we discussed previously. What does it mean? At the conduction band edge as well as the valence band. Okay. So the intrinsic carrier concentration of both the semiconductors is given at 300 Kelvin. It is of the order of 10 to the power of 10 for semiconductor A per centimeter cube. Let's be aware of the units, and it is of the order of 10 to the power of 7 for the semiconductor B. So from this, we should we are told to find the band gap of semiconductor B if we have been given the band gap value of semiconductor A. So what we have been given is that we have been told that the conduction band effective density of states are equal for both the materials. So let's put the conditions we are given. That is, the effective density of states for material A is equal to effective density of states for material B, semiconductor B, and they are both equal to some number Nc. Okay. Similarly, for Nv, Nv of A is equal to Nv of B is equal to a number Nv, which is some hypothetical number. And also we have been given the intrinsic carrier concentration, which is Ni of A, which is 1.5 into 10 to the power of 10 per centimeter cube. Okay. And Ni of B, that is the intrinsic concentration, carrier concentration of material B, is 3.2 into 10 to the power of 7 per centimeter cube. Okay. And also the band gap of Eg of A, material A, is given to be equal to 1.12 electron volts. So you must be aware that 1.12 is the band gap of silicon. So by just looking at two numbers, Eg of A and Ni of A, we can just quantitatively or qualitatively say that this material is silicon. Okay. Although many other materials can also have the same number, but till now what we have seen is that the silicon is a material which has a band gap of 1.12 electron volts, and intrinsic carrier concentration of the order of 10 to the power of 10 per centimeter cube at room temperature. Let's be uh, more precise about the terminology. Okay, at room temperature, it is Ni at room temperature. Okay, so we now know that whenever we derive this formula, Ni square is equal to Nc Nv times exponential of minus Eg by Kt. When professor did that in the lectures, we are going to use the same formula. We are saying that Ni is simply Nc Nv exponential of minus Eg by 2Kt. Okay. Now Ni of A and Ni of B will be two different intrinsic carrier concentrations that will be dependent on the Nc and V, that is conduction band and valence band effective density of states, and the band gap as well as the thermal energy. Okay, so Nc and V, we will write it like this. This is Nc of A, this is and this is Nv of A under the square root divided by Nc of B into Nv of B, material B, into exponential of minus Eg of A by 2Kt, exponential of minus Eg of B by 2Kt. Okay, so Nc of A and Nv of A, we know this is simply Nc Nv divided by root of Nc Nv. So both these quantities will go and we will be simply left with exponential of minus Eg of A minus Eg of B. This will be divided by 2Kt. Okay. So this is the result we have obtained till now. Now if we take the ln on both sides, let's get rid of this exponential, and we can clearly see that this will be ln of n intrinsic carrier concentration of A divided by intrinsic concentration of B is equal to minus Eg of A plus Eg of B by 2Kt. Okay, by 2Kt. Okay, or simply we can say that this Eg of B is simply Eg of A plus 2Kt ln of Ni of A, that is the intrinsic carrier concentration of material A divided by intrinsic carrier concentration of material B. So let's put the values for this Eg of A. That is the band gap of A is material A is 1.12 and plus 2 times this Kt at room temperature, that is 300 kelvins. We can take it to be equal to 26 milli electron volts. So this is 0.026 ln of Ni is 1.5 into 10 to the power of 10 per centimeter cube, 1.5 into 10 to the power of 10, and Ni of B is 3.2 into 10 to the power of 7, 3.2 into 10 to the power of 7. Okay, so let's solve for this. So ln of 6.15 into 2 into 0.026, so it's 0.32 plus 1.12, so it comes out to be equal to approximately 1.439 electron volts. That is the band gap of B. or simply let's check the options. So from this we can say that option B is matching with our results, so we can select this option B. Okay, so we will go with this option B because this is approximately equal to 1.44 electron volts. Okay, so let's move towards another problem. And this problem statement, let's read it first, says that the probability of a state being filled by an electron at some energy, which is EC minus KT, is equal to the probability of a state being filled by a hole, okay, at EC minus 3 KT. So we have been given that the probabilities are equal for two energy values. One is at EC minus 3 kT, that's 3 kT below the conduction band, and another is EC minus the whole energy. Another is for the whole probability. Okay, let's be clear about this statement. It's about the whole. So what it says that the probability of occupation of an electron is simply 1 divided by, that's what we have been doing till now, E minus AF by KT. Okay, this is the probability of occupation of an electron. Okay, so this probability of an occupation by hole is simply 1 minus this thing. So it is 1 minus this thing, and it will simply come out to be equal to 1 plus exponential of EF minus E by KT. Okay, it is just 1 minus of the probability of the electron, probability of occupation of an electron at a particular energy level E. Okay, so now this EC, this energy for electron, is given to be equal to EC minus KT, and for hole it is given to be equal to EC minus 3 KT. So what we have to do, we have to equate these probabilities because it has been given to us that the probabilities are equal for both the conditions. So from this we have to locate the Fermi level of the system. Okay, so what we will do, we will equate these probabilities, that probabilities of states being occupied, and it will give us simply 1 plus exponential of, for the electron it is EC minus KT minus EF by KT, okay, is equal to 1 divided by exponential of EF minus EC plus 3 KT by KT. So this one will go, this one and this one will go, and we will be simply left with the exponentials. Okay, so if we now take ln on both sides, let's go to another page and write it like this, taking ln on both sides, what we will get is, sorry, we will get this to be equal to EC minus KT minus EF. Okay, EC minus EF minus KT, EC minus EF minus KT by KT is equal to EF minus EC, EF minus EC plus 3 KT by KT. This KT and this KT will go, and this will be 2 EC minus 4 KT is 2EF. Okay, yes, it is EC minus 2KT is EF. So this is the location of the Fermi level, what we have found out. So let's check the options. So the options are that it is 3 kT above the valence band, which is not true. It is 2 kT below the conduction band, and it is uh, 2 kT below the conduction band. Okay, that's what we have got. Okay, so one of the options matched to our solution. So it is this Fermi level is 2 kT below the conduction band. Now moving to another problem, which says that this silicon wafer is doped um, with arsenic atoms. Okay, the arsenic atoms, they act as okay, what do they act as? They act as donor impurities. Okay, they are pentavalent. Okay, so if you whenever you feel that you are having some confusion, you are always welcome to look into the periodic table. Okay, so from periodic table you can clearly see that this arsenic is pentavalent. Okay, so it is having, just like phosphorus, it's having 5 electrons. Okay, so you can use this arsenic as a donor impurity. Okay, for the silicon material. Okay, so this arsenic will act as a donor impurity. Also, it has been given in the problem. Like for example, if they had not mentioned it to be donor, you could have easily figured it out by just saying that this is a pentavalent. This is having 5 electrons in its valence orbit, and as a result of this thing, whenever it bonds with this silicon atom, we will be having one free electron. And overall, they let me ask you one question, and let me check if you are active enough to answer this, and I feel you will be able to answer this. So if I have an electron that is now free, will there be some charge on my semiconductor as a whole? Can you comment on this? Because now I have free electron, and this free electron has a charge of minus e, let's say -1. In so, can you comment about the charge of the semiconductor? What will be the charge as a whole on the semiconductor? Will it be negatively charged? Will it be positively charged? Or will it be charge neutral? And why so? So you can either type in the chat as well in the message, or if you want to unmute, you can unmute yourself as well to if you feel that you can answer this question. Okay. Okay, semiconductor as a whole will be charge neutral, because this donor now will have a positive charge, and these donors, they are immobile ions. Okay, they won't contribute in the transport. Okay, because they are heavier and they are localized. Okay, they are localized, they are bonded to the silicon atom, and now since they have lost an electron, they will be acting as a charge site. Okay, as a positive charge site, Nd positive. Okay, for donor, and the electron will be moving freely. And now these donor impurities, what they will act also as a hindrance to the movement of the electrons. As you have seen in the lectures which professor taught us, he told that there will be impurity scattering. Impurity scattering, how does it come into the picture? It comes into the picture because of these donors or acceptors. Whenever an electron is free, it it tries to move through the, let's say, through we are having a material, let's say silicon MOSFET, and as electron is trying to move from source to drain, okay, and whenever it tries to go from this source to drain, let's say, okay, uh, if you see that if an electron is going from source to drain, let's say, then there will be some hindrance to its movement because of these charges, because these are positively charged, and positively charged sites, they will have some, you have seen that there will be some potential built around these sites, and as a result of these potentials they will influence the negative charge, and as a result of this negative charge will feel some hindrance to its moments, okay, as you have seen the mobility versus temperature curve as well. Whenever this charge spends a lot of time around the impurity, let's say electron is there in the semiconductor which is acting as a free carrier, and we have these donor impurities, and whenever the electron is in the vicinity of this donor impurity for a longer time, then this is the major governing factor. This deteriorates our mobility to a larger extent. And you have seen at low temperatures, the mobility is limited by these impurities. Okay. So at high temperatures, when we are having enough lattice vibrations, and as you have seen that the phonons or the quanta of those lattice vibrations, and those phonons are the major hindrances to the mobility, and they majorly govern our mobility at high temperatures. So basically what we were saying in this problem is that we are having these donor impurities, okay. These donor impurities are now located some 54 milli electron volts below EC, okay. So this is another important point over here, that this is very close to the conduction band edge, okay. There are two types of donors or impurities, okay. One is the shallow dopant and another is the deep dopant, okay. The deep dopant will be located far away from the conduction band edge, and for example, if it's a deep donor dopant, it will be located far away from the conduction band edge and towards the middle of the semiconductor, okay. That it will be towards the middle of the band gap. So those kind of states, you will see there was one problem also, and I guess it will be in the next assignment, I don't know, where you will be asked to find the trap efficiency, okay. So in that, you will see how these deep dopants act as the trapping sites for the materials, okay. So the donor level is 54 milli electron volt below conduction band edge, and we have been told to find out the percentage of the donor atoms that are ionized at 77 Kelvin, and the effective density of states at 77 Kelvin is given to be equal to 4.2 into 10 to the power of 18 per centimeter cube, and the degeneracy factor is given to be equal to 2, okay. So what we will do first, we will go to the charge balance itself, okay. So the charge neutrality relation, okay, says that the positive charge is equal to negative charge in a semiconductor, because the semiconductor has to be charge neutral as a whole, okay. There are no acceptor impurities, so Na minus will be equal to 0, and also the hole concentration will be very less as compared to the electron concentration, okay. So as a result of this thing, at 77 Kelvin, what we will write is, we will write this Nd positive to be approximately equal to N, because this is an N type material, okay. So the electron concentration will be very high. So we can also say that this N, which is the electronic concentration, in terms of the effective density of states, is simply given by exponential of EF minus EC by KT, okay. So this is the uh, what we can say, the concentration of the electrons. Now you must have gone through the lectures, and where you have seen that the ionized donor concentration is given. It's given by, let us use another slide, which is Nd positive is simply Nd divided by 1 plus Gd, where this Gd is the degeneracy factor, exponential of EF minus AD by KT. Okay, so let's do some manipulations. Okay, let's add and subtract conduction band H from this. Let's simply do this thing. 1 by GD exponential of EF minus EC, okay, plus EC minus AD by KT. Okay, we have what we have done. We have added and subtracted EC. Okay, so this ND positive was simply N. Okay, so N is simply ND divided by 1 plus GD exponential of EF minus EC by KT into exponential of EC minus ED by KT. We have what we have done over here is we have just split this exponential, okay, so that we can get this thing EF minus exponential of EF minus EC by KT. This exponential of EF minus EC by KT is simply this thing, N by NC is exponential of EF minus EC by KT. Okay, so let's put this over here. So it is N ND 1 plus GD N by NC exponential of EC minus ED by KT. Okay, so what we can do is now we can solve for this. This will be a quadratic in N, but let's do some manipulations to this thing. Okay, let's do some manipulations to this thing. Okay, so let me say that this whole thing, this GD and C exponential of EC minus AD is equal to X. Okay, let me put it like this. Let me put it like this. Let X equal to, okay, NC by GD exponential of minus times EC minus AD by KT. Okay, so the equation will become, it will be N equal to ND divided by 1 plus N divided by X. Okay, so the X is this thing. Okay, it will be now simply N plus N square N plus N square X is nd, n square n plus n square by x is nd. Okay, so now this nd, this nd, or simply it is n square plus nx minus nd is equal to 0. Okay, it has x over here as well. Okay, so the quadratic in n is simply minus b plus minus, so the concentration will be positive, so it is plus times b square is simply x square minus 4ac plus 4 times a is 1, c is ndx, so it is ndx divided by 2a, and a is 1. Okay, so now what we are going to look at, we are going to find the value for this x first, and this x, once we find this x, it will give us the value of this electron concentration. So for the x, what we need to find out, we need to find out this whole thing, nc by gd exponential of minus ec minus ed by kt. So let's look at the value of the temperature first. So the temperature is 77 Kelvin. Okay, temperature is 77 Kelvin. So kt needs to be found out at 77 Kelvin, and it is simply kt at 300 Kelvin, okay, into temperature of 77 Kelvin divided by temperature of 300 Kelvin. It's just other way around that I have done. I have not used the value of K and T to calculate the value of KT at 77 Kelvin. I have just done the manipulation that I will just say the value of KT at 300 Kelvin, use that value and divided by the 300 Kelvin temperature, which will give me the value of K, and then I will simply multiply it by the temperature of 77 Kelvin. So it will be simply 0.026 into 77 Kelvin divided by 300. So let's find out this value for this 77 Kelvin value temperature. The thermal energy, what will be the thermal energy? It will be 0.026 into 77 divided by 300. So it is 6.67 milli electron volts. Okay, 6.67 milli electron volts. Okay, so it is the value of the thermal energy at 77 kelvins. Now the value of x is Nc by Gd. Nc was equal to 4.2 into 10 to the power of 18 per centimeter cube at 77 Kelvin, the effective density of states. So it is 4.2 into 10 to the power of 18 per centimeter cube, and the degeneracy factor is 2 simply. Okay, and this has been multiplied by exponential of minus ec minus ed. ec minus ed is simply this value, 54 milli electron volts. This ed was located 54 milli electron volts below the conduction band edge. So it is now simply minus 54 milli electron volts divided by kt. kt we found out to be equal to 6.67 milli electron volts. Okay, 6.67 milli electron volts. So this milli electron volt and milli electron volt will go, and we will be simply left with this exponential of 54 divided by 6.67, 8.095. This is exponential of minus 8.095, 3.04 into 4.2 divided by 2. So it's 6.4 into 10 to the power of 14. per centimeter cube. It has the units of the same as the effective density of states, because this exponential will be unitless, this degeneracy factor is unitless, and the NC is having the units of per centimeter cube. So that's why this X is also having the units of per centimeter cube. Now N is simply this value, sorry, minus X. Minus X is simply minus 6.4 into 10 to the power of 14 plus x square. X square is 6.4 into 10 to the power of 14 whole squared plus 4 ndx. 4 times nd is 10 to the power of 16 per centimeter cube. Okay, it is given in the problem. 10 to the power of 16 into 6.4 into 10 to the power of 14 divided by 2. So let's take this 10 to the power 14 outside, and we will be left with 6.4 into 10 to the power of 14 plus 10 to the power of 14. It is simply, let's calculate it, and it comes out to be equal to 2600.96. Okay, divided by 2. So let's square root this thing and let's add up these two, and it will be simply equal to 44.6 into 10 to the power of 15 divided by 2 per centimeter cube, or N is simply equal to 2.23 into 10 to the power of 15 per centimeter cube. So we have found out the concentration, this electron concentration that have been ionized. Okay, so from this, what we can do, what we have to find out, we have to find out the percentage of donor atoms that are ionized. Okay, so we have got this number, which is 2.23 into 10 to the power 15, and total donor impurities was 10 to the power of 16. So the percentage is simply, therefore, percentage of donor atoms ionized is this N divided by Nd into 100. This is the percentage. Okay, so it's 2.23 into 10 to the power of 15. 2.23 into 10 to the power of 15, and Nd is 10 to the power of 60 into 100. So this will go, we will be left with this thing only, and it is 22.3%. Okay, so it's 22.3%, and option C is matching our results, so we will say we have got the correct option. Okay, so it is 22.3% of impurities they have ionized. Okay, completely. So this is not the complete ionization case, because the thermal energy is very less. It is 77, at the temperature is only 77 Kelvin. As a result of this thing, only 22%, approximately 22% of the impurity atoms got ionized. So you can clearly see in this example how the temperature can affect the number of ionized impurity atoms. Okay, so this largely depends on the thermal energy. Had it been the 300 Kelvin, the answer would have been quite different, and you could have got more number of ionized impurities. Okay, because of the high thermal energy. So in this case, only 22%, approximately 22% got donor atoms got ionized. Now moving to another problem, which says that we have a semiconductor with density of states given. This in this problem, the density of states is a linear function of energy, as you can say that gc of E is simply A times A is a constant, E minus EC, okay, and A times E minus EC, it simply means that the states are linear function of energy. And Gv, which is the density of states in the valence band, they are also linear function of energy with a negative slope considering the B is positive, okay, if B is positive. And this clearly says that we are having the density of states, which is a linear function of energy for the two materials, okay, and where these A and B are non-zero constants. What we have to do, we have to assume first this Boltzmann distribution for both type of carriers, and we have to consider the reference potential energy level as the valence band, and EC is the energy at the conduction band. We have to compute the intrinsic Fermi energy level, okay. So uh, as professor taught us in the class, what we did there was that whenever we are going to find the concentration of the electrons or the holes that are present in the conduction band or the valence band, we are going to multiply the density of states that for example in 2D case we solved, in 1D case we also solved, and also in the 0D case professor taught us, okay. So what we do is we simply say that we will multiply the number of states with the probability of occupation and integrate it over the whole energy. That's what gives us the total carrier concentration, okay. So that was done by the professor in the lectures. So what we will do over here, we will do the same thing. We will say the density of states in the conduction band is simply A times E minus EC, and the density of states in the valence band is simply B times, sorry, V times EV minus E. Okay, these are the density of states in the conduction band and the valence band. Now, what we have been told, we have been told to use the using Bolt Boltzmann distribution. Okay, we have to use the Boltzmann distribution for both type of carriers. So, for the electrons, it is simply 1 divided by the, so sorry, so we have not used the Fermi, we have to use the Boltzmann. So it means that E is that this E minus EF is greater than 3 kT, okay, much greater than 3 kT, okay, that is the condition for this. E minus EF by kT, okay. So we can say that E minus EF is much greater than 3 kT. That's when we can use this formula and we can neglect the 1 plus that was there in the Fermi-Dirac distribution, that when we solved in the previous problem. Let's go to the previous problem. Okay, here whenever this E minus EF is much greater than 3 kT, then we can safely ignore this one. Okay, we can safely ignore this one, and this exponential will be simply now exponential of minus E minus EF by kT. This will be simply this probability of occupation will now be given by the Boltzmann distribution for that case. Okay, that's what we have done. And for holes, we will simply say it is FH of E is simply, sorry, So sorry, for now let's write again for holes. For holes, it is fh of E is equal to exponential of E minus EF by KT. Using this similar argument that E minus EF is much greater than KT. Okay. Uh, so now the concentration is simply equal to this N. This N is the concentration, and it is simply equal to, there is no states in the band gap, so we will start the integral with from EC, because there are no states in the band gap. Okay, there is no GC of E in the band gap. GC of E itself starts from the EC. Okay, so it is simply GC of E times the probability of occupation of these electrons dE. Okay, so it is simply now EC to infinity, this integral GC of E is A times E minus EC. Okay, it is A times E minus EC. Okay, this is the value of GC of E, and F of E is simply exponential of E minus EF by KT. Okay, now let me do some manipulations. Let us add and subtract EC. Add and subtract EC. Okay, so N is simply two exponential. Let me be clear. Okay, exponential of minus E minus EC plus EC minus AF. Okay, by KT. It will just help us to solve this problem much easily. Okay, so it is now simply A times EC to infinity E minus EC exponential of minus times E minus EC by KT. Okay, times exponential of minus EC minus EF by KT. Okay, this term is independent of energy, independent of energy, and hence we can take it out of the integral, and we can write this N to be equal to A times exponential of minus times EC minus EF by KT. EC to infinity E minus EC exponential of minus times E minus EC by KT D of E. Okay, that's one thing what we got over here. Let's insert the slide, and let us say this E minus EC by KT is equal to X. Okay, we are doing some substitution, so it will imply DE is simply KT times dx, and the limits when E is equal to EC, X is 0, E equal to infinity, X equal to infinity. So these are the limits. Limits are now, so it is A times EF minus EC by KT. Okay. Integral 0 to infinity. 0 to infinity. 0 to infinity. Let us check. E minus EC is simply KTX. E minus EC is simply KTX. Okay. And this is exponential of minus x. Exponential of minus x. And dE is simply KT dx. Okay. KT dx. So it is simply a times exponential of EF minus EC by KT into KT squared 0 to infinity x e minus x dx. So if I solve this integral now, it is simply x e minus x minus 0 to infinity is 0, is plus e to the power of minus x, 0 to infinity, it is minus e minus x, 0 to infinity are the limits. So at infinity it tends to 0. So the value of this integral is simply 1. Okay. So the value of this integral is simply equal to 1. Okay. This integral, this whole integral, just using UV rule. Okay. So n is simply now equal to, n is simply now equal to, n is equal to a times KT squared exponential of EF minus EC by KT. Okay, that's what we got for the electron concentration. Now for the holes, it is same. The holes are there in the valence band. So the limit will start from minus infinity and end at EV. So let me be clear, it's not actually minus infinity. We have taken it to be equal to minus infinity because we know that this Fermi distribution or the Boltzmann distribution, it is a decaying distribution. Okay, so even if it is for example 7 EV value, for example it is around EV plus 10 KT, this Boltzmann distribution will decay down. Okay, this Boltzmann distribution will decay down, and as a result of this thing, it is immaterial whatever the lower limit of this integral is, because we know that it will, this Fermi distribution or the Boltzmann distribution, it is going to decay with the energy. Okay, so it is immaterial to us. Okay, as a result of this thing, we can take this limit to be equal to minus infinity, and we can say the upper limit is EV, which is the valence band edge, and this is what professor also taught us in the class. So this is simply equal to GV of E, which is the density of states in the valence band, times the probability of occupation, which is given by the Fermi, in this case it is given by Boltzmann distribution, because we have been told to assume it like that E minus EF is much greater than KT, or much greater than 3 KT. Okay, 3 KT is a safe number to play with. Okay, so this GV is simply equal to, B times EV minus E. Okay, it is minus infinity to EV, B times EV minus V, and this F of E is simply the probability of occupation of hole, which is E minus EF by DE. Okay, that's what we have got, and we can use this similar argument. We can similarly add and subtract this EV from the expression, and we can say we can simply say that we will use this, we will add and subtract like what we did in the previous, for this n concentration, subtract EV from exponent, okay, exponential. So what we will get is, we will simply get, taking b times exponential of EV minus EF by KT with limits minus infinity to EV minus E, exponential of minus E minus EV by KT. I have done 2 or 3 steps in just one step because we did it previously. What I have done, I have added and subtracted EV, and I have taken this energy independent term outside because it is independent of energy, independent of E. Okay. Now uh, let us use this EV minus E by KT equal to Y. Okay, what will it give us? It will give us dE is simply minus KT dy. Okay, also when E tends to minus infinity, Y tends to plus infinity, and as E tends to EV, Y tends to 0. So the limits of this thing will be, simply it is b times exponential of EV minus EF by KT. So the limits will be minus infinity goes to plus infinity, okay, and EV goes to 0, okay, and this EV minus E is KT times Y, okay, and this thing E minus EV by KT is simply minus Y. So it is now exponential of minus Y minus KT dy. Now making the limits same as the previous problem, it would simply be b times KT squared exponential of EV minus EF by KT. The limits, now let's flip the limits, so it is 0 to infinity, and as a result of this thing, this minus will go, okay, minus and minus will become plus, and we will be left with y times e to the power of minus y dy, and this value, what we found out, x times ex 0 to infinity dx is 1, so this value is equal to 1, and the P, which is the whole concentration, is now simply equal to B times KT squared times this exponential. This exponential is simply exponential of EV minus EF by KT. Okay, so it is exponential of EV minus EF by KT. So this is for the holes. So let us put it in the bracket, sorry, in the n circle. Let's encircle it, and now let us see what the problem meant. Problem wanted us to find the intrinsic Fermi level. So the intrinsic Fermi level needs to be found out when A is equal to 2 times B. So for intrinsic Fermi level, we know that for intrinsic Fermi level, the electronic concentration has to be equal to hole concentration has to be equal to intrinsic concentration. Okay, and for that EF, which is the Fermi level, is the intrinsic Fermi level. The Fermi level is the intrinsic Fermi level. So we have found the value of N and P. We have to equate those N and P, and came out to be equal to A kT square exponential of EF minus EC by kT. And N is, so N is A times kT squared exponential of, sorry, let me check once again, EF minus EC by kT. EF is EFI now, okay, EFI minus EC by kT is equal to P. P came out to be equal to, sorry, it is B times kT square, not 2B times. It is B times kT squared exponential of EV minus EF by kT. Okay, so this kT square and kT square will go, and this A I guess is 2 times B. A is 2 times B, so it is 2B exponential of EFI minus EC minus EV, so this is EFI plus EFI by kT is B. So B and B will go, and we will take ln on both sides, applying ln on both sides. What we will get is, we will get 2 times EFI minus EC minus EV is equal to ln of 1 by 2 times kT. Okay, so EFI is simply EC plus EV by 2 plus kT by 2 ln of 1 by 2. So we have got the value for the intrinsic Fermi level in terms of EFI, EV and kT. Okay, ln of 1 by 2, let me calculate it, and let me also calculate the value of this kT times this thing. Ln of 0.5 is simply minus 0.69 into 0.026 divided by 2. It is coming out to be equal to 0.009 electron volts. So it is, sorry, so it is EFI is simply EC plus EV by 2 minus 0.009, and this is in electron volts. This the whole thing is having units of electron volts. Now let's check the options. Okay, there is no EV over here, so let's read the problem. Okay, EV has to be equal to 0 because it is taken as the potential reference energy. Okay, reference potential energy. So EV is equal to 0. So this EFI, okay, let us insert some slide. So since EV is a reference potential energy, therefore EFI is simply EC by 2 minus 0.009, okay, minus 0.009 electron volts. So it is option A, I guess. Okay, Yes, it is 9 milli electron volts. That's what we got. Okay, that's what we got. It is EFI is simply EC by 2 minus 9 milli electron volts. So we have found out for this material the value of the intrinsic Fermi level. Now let's move to another problem statement. Let's read it out first. It says that wait a second, let me have some water first. So it says that we have some electronic concentration profile. Okay, this electronic concentration, it varies linearly as is shown in the figure. Okay, this figure shows the variation. Sorry, let me use red. This figure shows the variation of the electronic concentration. The electronic concentration is decreasing as we go from x equal to 0 to x equal to L. So it is given by some linear equation uh, in one variable, and uh, we need to find out the equation of this line first. Given that the concentration of electron at x equal to 0 is n, and at x equal to L the concentration is 0. So we have to calculate the total number of electrons which are present in the material given the cross section A. Okay, so let us find out the this n of x is simply linear equation a plus bx. Okay, so what is at x equal to 0, the concentration is n, so n is equal to a. Okay, a we get to be equal to n. Now at x equal to L, concentration is 0. Okay, if concentration is 0, so it means 0 is equal to a plus bl. Sorry, it is b times n, not b by l. Or b is simply minus n by l. Okay, so the equation for this electron concentration is simply this thing, n minus 1, n minus n by l. It is n minus n by lx, or simply it is n times 1 minus x by l. Okay, so the total electron concentration needs to be found out when we have been given the area to be equal to a. Okay, the total number of electrons is simply total electrons is concentration times the volume. We know n of x is per centimeter, so it is simply a times 0 to L, L is the limit, n times 1 minus x by L dx. So it is simply a n, this is x, 0 to L, minus times x square by 2L, 0 to L. So it is a n L minus L square by 2L, which is simply a n L by 2. So this is the total electrons present in this what we can say in this profile what we have been shown. So it is option C. Okay, So it is option C, which is matching with our results. Now we have another problem statement which says that the semiconductor has the following properties. The diffusion coefficient of electrons is 25 centimeters square per second, and the diffusion constant for the holes is 10 centimeters square per second. The lifetimes for the electron and hole is given to be equal to 1 and 1 microsecond and zero point 0.1 microsecond. The semiconductor is p type. Okay, if the semiconductor is p type with Na, that is acceptor doping of the power of 10 to the power of 17 per centimeter cube, and it is held in equilibrium for some time, for a time which is less than 0. Okay, we start at t equal to 0. Okay, and at t equal to 0 an external source is turned on. This external source can be anything, like for example a light generator. Okay, we are just using a light, shining a light on the semiconductor bar. Okay, and this produces the carriers at the rate of 10 to the power of 20 centimeter cube per second. As a result of this thing, there will be some generation, and after 2 microseconds the source is turned off. Okay, and the source is turned off at 2 microseconds. So if we turn off the source at 2 microseconds, there will be now, we can say, the recombination of the carriers. So what is the excess carrier concentration at 2 microseconds? We have to find out the excess minority carrier concentration, because since it's a p type, minority carriers are electrons. Okay, minority carriers or electrons, because it is a p type. So the so let's write down the continuity equation. You must have seen, in terms of the diffusion coefficient, it is dn d square delta n, where del n is the excess electron concentration, dx square, plus mu n is the mobility, E is the electric field, d by delta n by dx plus gl minus delta n by tau n naught is equal to delta d by delta n dt. Okay, so first of all, this term will be 0, this term will be also 0, because E is equal to 0, no field. Okay, also this is uniform generation, so the variation with the x for this thing is this excess carrier concentration is 0. Sorry, so this is also 0, because uniform generation. Okay, now we are left with the term which is GL, which is the generation rate, and dn by tau n, which is the recombination rate, and it is given by delta by dn by dt, the variation of this excess carrier concentration with the time. How does it vary with time? So this equation looks familiar. Okay, it can be, we can just write this equation to be equal to d by delta n by dt plus delta n by tau n naught is equal to gl. Okay, this equation is similar to the form kind of dy by dx, which is Bernoulli's equation. Okay, you must have seen it in your 11th and 10th class, 11th and 12th class, while solving the differential equations. is equal to q. It is of the form of this is of this form. Okay, so p here in this equation is 1 by tau n naught. Okay, and q is simply this generation rate gl. Now integral p dt, x is simply this t here and y is simply delta n. Okay, so integral of p dt is simply dt by tau n naught is simply t by tau n naught. Now the integrating factor is simply exponential of integral p dt. It is simply now exponential of tau by tau n naught. Okay, so the solution is for this kind of equation is simply y times the integrating factor equal to integral of q times integrating factor dx plus the constant c. Okay, so y in our case is delta n, integrating factor is exponential of t by tau n naught, q is gl, and this integrating factor is t by tau n naught, and dx is simply dt c. Okay, let's insert some slides. So it is simply delta n exponential of t by tau n naught is simply tau n naught gl, yes, tau n naught gl exponential of t by tau n naught plus c. Okay, absolutely correct. Now at t equal to 0, at t equal to 0 there is one special condition. What is it? It is that we are having no excess carrier concentrations, that is this dn is equal to 0 at t equal to 0. So what we will get is we will get okay, we will get this thing at t equal to 0. This is 0, this is tau n naught gl, exponential of 0 is 1 plus c, or c is simply minus tau n naught gl. Okay, absolutely, yes, that's what we have got. Is it correct? Yes, it is correct. Okay. So delta n exponential of t by tau n naught is simply equal to tau n naught gl exponential of t by tau n naught minus 1, or simply this excess electron concentration is simply equal to tau n naught gl 1 minus exponential of minus t by tau n naught. Okay, this is what we got for the excess electron concentration, the expression of this delta n as a function of time. Now let's look into the values of this tau n naught gl, which is a generation rate, and let's try to find out it at 2 microseconds. Okay, gl is 10 to the power of 10 to the power of 20. This is the generation rate. So it is, let me write it like this, gl is 10 to the power of 20 centimeter cube per second. Tau n naught is the lifetime for these electrons, and it is 1 microsecond. Okay, tau n naught is 1 microsecond. So we have these both these values, so we can clearly say that this dn, this is excess carrier concentration at 2 microseconds, is simply 1 microsecond which is 10 to the power of minus 6 into 10 to the power of 20. So it will give me centimeter cube times 1 minus exponential of minus 2 microseconds divided by 1 microsecond. So microsecond and microsecond will go. So it will be 10 to the power of 14 times 1 minus exponential of minus 2. Okay. So it is exponential of minus 2 minus 1.865. So it comes out to be equal to delta n comes out to be equal to 8.65 into 10 to the power of 13 per centimeter cube. So this is the excess electron concentration at 2 microseconds when we have just turned off this source. Okay, so let's check. Option A is, I guess, matching 8.65. So we have done everything correctly. Okay, now let's move to another problem which says that we have an intrinsic wafer, silicon wafer, and it is doped with donor impurity of the order of 10 to the power of 16 per centimeter cube. Okay, it has been doped of the order of 10 to the power of 16. Over here it is written, sorry, 10 to the power of 16 per centimeter cube donors. And now we are using some photons, we are irradiating it with some photons of the order of 10 to the power of 12 per second on the silicon volume. Okay, and we assume that each photon generates one electron hole pair, and under this light illumination we have to find the location of the Fermi levels with respect to the intrinsic Fermi level. Okay, as you have seen in the lectures, professor taught us that the intrinsic Fermi levels, when we are doping, for example, a material, uh, we will be having these different Fermi levels for electrons and different Fermi level for holes, and those Fermi levels were known by the name of quasi Fermi level. Okay, they were known by the names of the quasi Fermi level because they under this illumination, for example, whenever we are illuminating it with light and we are generating electrons and hole pairs, this electron and hole pair generation for example an n type material, for example, if donors are of the order of 10 to the power of 16 and we are doping it of the order of we are using the light of the by illuminating 10 to the power of 12 photons per second, let's say, as is the case here, we will not be able to generate enough electrons. Okay, the electronic concentration will still be governed by the donor impurities because donor impurities are larger in number, and as compared to this, the hole concentration will increase drastically because the hole concentration, if we consider Ni to be equal to the 10 to the power of 10 as is the case here, the hole concentration will just be of the order of 10 to the power of 4 per centimeter cube. But when I am illuminating light and I am creating electron hole pairs, the holes have increased from 10 to the power of 4 to 10 to the power of 12. As a result, the whole Fermi level will drastically change as compared to the electronic Fermi level. So let us write it down like this. The majority carrier concentration is simply N naught, and D is 10 to the power of 60 per centimeter cube. Okay, minority carrier concentration, which is holes, in this case I am considering thermal equilibrium first. Okay, minority concentration P naught is simply Ni square by Nd is equal to 10 to the power of 20 by 10 to the power of 16 is equal to 10 to the power of 4 per centimeter cube. Okay. So the position of Fermi level at thermal equilibrium we can simply find out. Sorry. So the position at thermal equilibrium is simply given by EFN minus EI is simply KT ln of N naught by Ni. This is with respect to the intrinsic Fermi level. Okay, it is simply at 300 Kelvin. It is 26 milli electron volts ln of 10 to the power of 16 by 10 to the power of 10, which is ln of 10 to the power of 6, ln of 10 to the power of 6 into 0.026. Let me calculate it, and it comes out to be equal to 0.36 electron volts. Okay, now for holes in thermal equilibrium, it is EI minus EFP KT ln of P naught by Ni. It is simply 0.026 ln of 10 to the power of 4 by 10 to the power of 10. It is simply 10 to the power of minus 6, minus will go outside, it is minus 0.36. Okay, so that's what we have found out. The Fermi levels are uh, uh, just 0.36 electron volts above this intrinsic level. Okay, and in the thermal equilibrium. Okay, let me write it down like this. The Fermi level is 0.36 electron volts above intrinsic energy. Okay, this is in the case of thermal equilibrium. Now, under this light elimination, what happens is the system moves away from this thermal equilibrium, and we will need different Fermi levels to capture electron and concentrations. Okay, so now what we are going to do is we are going to solve for the under the illumination. We are going to find out how does the Fermi level change. So if we assume now this light illumination has taken place and it generates photons of the order of 10 to the power of 12, and each photon generates one electron hole pair. So let's write it down like this. Light illumination generates 10 to the power of 12 per centimeter cube electron hole pairs. Okay, so delta n is now, and delta p is simply 10 to the power of 12 per centimeter cube. That is the excess electron and hole concentration generated by this light. So the electronic concentration will now be simply the equilibrium concentration plus this delta n. The electronic equilibrium concentration was 10 to the power of 16 per centimeter cube, and delta n is simply 10 to the power of 12, and we can safely say this number is equal to 10 to the power of 16, because 10 to the power of 12 is much less than 10 to the power of 16. But for P, what has happened, P plus delta P naught plus delta P naught was 10 to the power of 4. Now delta P has increased to 10 to the power of 12. So this number, this whole concentration has okay, no problem. You can watch the recording later, okay? No problem. So the whole concentration now has increased to 10 to the power of 12. Earlier in the thermal equilibrium, it was just 10 to the power of 4. Now because we have illuminated it or irradiated with light, which is generating 10 to the power of 12 photons per second, and as a result of that thing, we are having 10 to the power of 12 per centimeter cube holes generated. So this number now will drastically affect the location of our Fermi level. So as now we have to look at the position of Fermi level. After light illumination. So the EFN minus EFI will remain same because the electronic concentration has not changed. It is KT ln of N naught by Ni, and it is 0.026 ln of 10 to the power of 16 by 10 to the power of 10, and it is same number what we got, 0.36 electron volts. Now the intrinsic this quasi Fermi level in case of these holes, with respect to the intrinsic Fermi level, it has changed drastically because the whole concentration now is P. It is not P naught. P naught was the equilibrium hole concentration, and this P now is 0.026 is the thermal energy. Okay, ln of P now is 10 to the power of this number, 10 to the power of 12. So it is 10 to the power of 12 divided by 10. So it is 10 to the power of 2 ln of 10 to the power of 2. Let's calculate it into 0.026, and sorry, this is 10 to the power of 10. So it comes out to be equal to 0.12 electron volts. So what have we deduced from it? That we require two different Fermi levels to capture non-equilibrium statistics, non-equilibrium situation. Okay, so we require this quasi-Fermi levels in case of this light illumination case. Okay, so the option B seems to be the reasonable option to go with. Okay, so I guess this is it from my side for today. In this problem, what we saw was that we will require two different Fermi levels in order to capture the non-equilibrium statistics. So we have gone through that. In the thermal equilibrium, we required the Fermi level to be equal to 0.36 in both the cases. And in the previous problem, what we did, was that we found out the electronic excess electron concentration. We just used the continuity equation and found out how the generation and the recombination rate will govern this process and help us to find the how does the excess carrier concentration change with time. And we found out at time to equal 2 microseconds, when we just turned off the source, the concentration of excess electrons. Similarly, for this problem, what we found out was the total electrons which are present in the, wait a second, there is some questions. Sir, in previous semester I have done the same, but I couldn't clear the course. Also, I have gone through the assignment but couldn't get the same. Sir, now how should I prepare to clear the course? Okay, so I would still recommend solving. Okay, so let me close the chat. Okay, so I would still recommend solving the numerical problems which professor is giving us. But apart from that, what this is not from the, since I'm not going to grade any paper. Let me be clear about this thing, and I'm not going to prepare any question for you. Okay, so if I have been at your place and I had to solve or I had to start any device physics course like this, and for example I am not having a good time in this course, then I will always try to solve the problems from Robert Pirret. Okay, semiconductor, you can always search for this book and you can find it. There is one book by this great author, which is Robert Pirret, and you will find there are two parts for this. Don't go for the advanced one, just start with the basic one. Okay, you will find a lot of problems and lot of examples in that. That will clearly help you in your device physics. That the quantum physics part is present in the advanced physics one, but I don't think that is much part of your course. Okay, that is just the first week of lecture, and there will be just one question from that. And apart from that, if you want to clear your device physics, whether it is p-n junction, okay, so it's by the Robert Pirret. Okay, okay, so you can solve the problems from that. Okay, I myself like that book a lot. It is the Semiconductor Device Fundamentals. Okay, you will find it anywhere. You can even buy that book. I recommend buying that book. So if you solve that book problems, there are some good examples as well, and as well as there are some problems which are unsolved, and you will build lot of concepts while solving regarding p-n junctions, regarding BJTs, regarding MOS capacitors, regarding MS junctions, which you will study in the upcoming, I guess in module 5 there will be metal semiconductor junction. Okay, so I recommend going through that book and solving the problems from that book, not solving it by just mugging up, but you just try to understand all the problems, and I guess you will do wonders in this course. And the circuit part, that is also not much of this course. There is Professor Behzad Razavi. They are the best books in that. But I would say if you are mostly oriented towards device physics, then Robert Pirret is a good thing. Okay, so let me recap the problem. This in this problem, what we did, we found out the electronic concentration and the hole concentration. We were told to find the concentration by solving for the using this Boltzmann approximation, Boltzmann distribution, and we saw that E minus EF has to be much greater than KT for this approximation to hold. And this density of states in this case was linear density of states, because it was linear function of energy. Okay, so we found out the how does the electron concentration will look like for this case, and it came out to be equal to some A times A was a constant times this KT squared times exponential of EF minus EC by KT. Okay, so that was this problem. And in the previous problem, the problem before that, we found out how many donor atoms got ionized, and it was quite simple to start with. We started with this charge neutrality relation, and from that we used the formula which professor taught us in the class. And this problem was quite straightforward. We had to just equate the two probabilities to find out the Fermi level location. And the first problem, which was about the two semiconductors. We just used the intrinsic carrier concentration formula and just divided the intrinsic carrier concentration of the two materials in order to get the band gap relations, because the effective density of states for both the materials was, for the conduction band and the valence band, was equal. So I guess that's it from my side. And if you have any question, you can ask. Otherwise, you can end the session. And also, as I had said previously, that if there is any question that you want me to solve, you just can drop. You can just drop me an email, and I will solve that a priori. And in this session, we will discuss that. Okay. So if we have no further questions, we can end the session. Uh, it is on Sunday. My live class will be on next Sunday now, from 3 to 5. Okay, so you were saying, but course teacher has a live class or not? Course teacher means Professor Sanjeev Sambhadan. No, I don't think so that there will be live classes from the professor. They are itself available as the recordings on the platform. You can access those anytime. Course teacher does not have a live class. Okay, so let's end the session. Thank you for joining.